Hi and welcome to the video. In this video we're going to talk about how to handle irregular field shapes when doing a hand calculation. So first let's talk about what an equivalent square is. Not all fields are going to be square. In fact, very few of them are. We'll often have either a rectangular shape or an asymmetric rectangular shape if we're talking about the jaws, or the MLCs may be used to shape any type of shape. When we're doing hand calc, we've got to be able to do a calculation despite not having a square field. So we define this equivalent square, which is a square field where the x jaws equals the y jaw size, that gives the same central axis depth dose characteristics as that of an irregular or a blocked field. And this can be applied to rectangular and asymmetric fields as needed. The general principle that we use to calculate this is that the equivalent square field size is equal to 4 times the area divided by the perimeter, where these are the area and perimeter of the field shape. So what does this look like for a rectangular field? Well, we start with our principle, and we know that the area is going to be the width times the length, and the perimeter is going to be 2 times the width plus 2 times the length, and we can put this together and get an equation that's the equivalent square for a rectangular field. And we can just look at one quick example of this. So let's say we have this rectangular field here. We know our equation here. The field size in the x dimension is 20 cm. The field size in the y dimension is 5 cm. And as we put this together, we can get an equivalent square field of 8 cm. And as you calculate that, one way to just do a sanity check is just to make sure that that field size, the equivalent square field size, is somewhere between the two field sizes, right? The x jaw is larger, the y jaw is smaller, so we're somewhere in the middle, which makes sense. What about circular fields? So we can determine the radius of an equivalent circular field, assuming that the circular field will have the same area as an equivalent square. So what does this look like? Well, we have the area of a circle, the area of a square. We can put those equal to each other, where here E sub SQ is the equivalent square field, and R EQ is the radius of the equivalent circular field. And if we solve for that, we can see that we get this relationship here, which if we put this back into our area versus perimeter, we can see that we get a very similar relationship for area and perimeter for a circular field that you can just derive using this this principle of putting the areas of the two fields to be equal. All right, what if we have fields that are irregular, not rectangular at all, right? So these would be shaped typically by the MLCs, and here's a couple of examples. We have a femur field on the left, a supraclavicle field in the middle, and then a tuber bed boost on the right. And note that these are all very common examples. This is probably it's probably going to be most common that you have some type of irregular field like this. So how do you calculate the field size in this case? Well, we can use what's called Clarkson's integration method, in which the field is divided into angular sectors, and the average field size is computed over all 360 degrees. The average field size can account for block sections as well as missing tissue if needed, and this may be automatically calculated for computer-based hand calculations, right? So your software may just automatically calculate this. You may not see it, or it can be done by hand if you so desire. Let's just look at a couple of examples. Here I've just made a very simple example where we have 4 quadrants, right? You can see that 3 of those quadrants have an effective square field size of 20 by 20, so it's 10 cm on a side. And then the 4th quadrant has an effective field size of 10 by 10, so it's 5 cm on a side. And so if we were to use the same principle as that's used in Clarkson's integration, we're basically dividing this into 4 categories, and you're kind of taking the average field size of those. And so we end up with an average field size per quadrant of 17.5 cm, which would make some sense, right? It's between the two values there, 5 cm or 10 cm field size and 20 cm field size. This field size would then be applied to the phantom scatter factor, right? Because this is what is applied to the MLCs versus the jaws. And then for the collimator scatter factor, you would just use the jaw field size. Let's look at another example, also simplified, but maybe a little more realistic, where we have kind of a more circular field shape here, which I guess it's not that realistic, but we'll go with it. We have 3 quadrants that have circular field size with a radius of 5 cm. And then we have 1 quadrant that has a circular field size with a radius of 10 cm. And we can kind of go through what the Clarkson's integration method would be. Basically, you're going to look at what the radius is all the way around, like maybe every 5 degrees or every 10 degrees or every 20 degrees, and just basically divide it into these angular sectors and calculate what the radius is at any of those, right? And for this case, 3/4 of these measure 5 cm and 1/4 measure 10 cm, so then we can get the average distance to the field edge being 6.25 cm. Now note that that's the equivalent circular field, right? We can then calculate the effective square field size using our relationship that we showed earlier. And here's just a demonstration of that, right? So this Clarkson's integration, you're going to just go around, and here I've done it for half of the field, but you would do it for all the entire field. Basically every 5 or 10 degrees, you're just measuring that and taking the average. Here we're able to simplify it into basically 4 numbers because the numbers are the same for each of those quadrants. Each of those quadrants basically has the same number continuously for that quadrant. All right, thank you.